The human heart is a four-chambered pump whose only purpose is to send blood to the rest of the body. It beats about 70 times per minute, day after day, year after year. 7 decades and some 2.6 billion beats later, it has pumped about 200 million liters of blood without lubrication or maintenance. But what happens when the heart becomes diseased and starts to malfunction? Every year, hundreds of thousands of people develop life-threatening problems directly related to the malfunction of the valves in their heart. At best, their quality of life is greatly diminished. Over the past decades, many of these patients have been saved by a difficult and traumatic open-heart operation performed by cardiac surgeons in specialized operating rooms. During this highly invasive operation, the patient undergoes general anesthesia, sawing through the sternum, bypass pumping, opening the myocardium, excising the diseased heart valve, implanting a new artificial valve, followed by days of intensive care and weeks of slow rehabilitation. The average risk of such operations is about 5%. Despite the extraordinary advances in open-heart surgery, about 30% of these patients face a much higher risk. Another 25% are not able to be operated at all because of their age or other risk factors. For these last two groups of patients, a revolutionary treatment option is more than overdue.
We have started the era of the interventional cardiology called the structural heart disease treatment. So really the introduction of the percutaneous valve replacement is a new step forward, and the challenge to introduce by a vessel in the groin has been made, and that's a real step forward.
At the CoreValve Research and Manufacturing Facility in Irvine, California, scientists and engineers are working together with leading physicians on the vision of replacing heart valves without surgery. Their focus is on the development of a system for replacing an aortic valve by a percutaneous approach on a beating heart. The CoreValve revalving system realizes this vision. It consists of 4 components. The most important is the self-expanding multi-level nitinol frame on which a porcine pericardial tissue valve is mounted. This bioprosthesis is loaded into a delivery catheter by means of a disposable loading system. The quality of the pericardial tissue and its preparation is crucial for the human compatibility and for the long-term durability of the artificial heart valve. The nitinol frame, which will be anchored in the patient's heart, must withstand high aortic pressures without deforming or moving. As a permanent implant, the production process must meet the most stringent manufacturing requirements, and CoreValve microbiological testing is rigorous. Final assembly takes place in a sterile environment. Absolute employee conscientiousness and accuracy are the utmost priority. They form the basis of reliability and years of full functionality of the CoreValve bioprosthesis. The engineering group uses test equipment that perfectly simulates the conditions in the human heart. Advanced control and data acquisition methods are used to monitor valve function and integrity. After completing successful in vitro testing, as well as undergoing cadaver and animal studies, the CoreValve revalving system successfully completed multi-phased human feasibility and safety studies during 2004 and 2005. The continuing challenge for CoreValve development engineers is the further reduction of the delivery catheter's diameter.
I think the CoreValve system itself appears to be very elegant, appears to be miniaturized, and most